That's right. Okay. So what we're doing here, we're moving on to the binomial distribution. Now, in G1 specifically, I think we're looking at the binomial distribution formula. So we have a formula we're going to use. And then in G2, we'll start to look at using our calculator for multiple outcomes and so forth. So to begin with, we have a formula, and then a bit later we'll use our calculator. Now, what a binomial experiment is it's a Bernoulli experiment. So there's two outcomes, success or failure, but it's repeated. Okay, so remember Bernoulli means just one trial. In a binomial distribution, we repeat the experiment. However, the probability must remain the same. We don't change the probability. So that means the trials are, the language that's used here, the trials are independent. So independent means one trial doesn't affect another trial. The probability remains the same. Okay, we've got Pascal's triangle there, and I think you guys are experts at drawing that. But we're going to point out a relationship between Pascal's triangle and some of the questions today. Here's the binomial distribution formula. Basically, we have the probability that the random variable, that the binomial distribution, takes on this number of successes. K is our number of successes. It's equal to the number of ways that we can have K successes given n trials. That's from Pascal's triangle. And then we have multiplied by the probability of success to the number of successes, multiplied by the probability of failure to the number of failures. Okay, so that's going to be our formula, and we're going to hit that in the test. We'll hit that in this exercise. So we have an unfair coin has a probability of landing on heads of 0.53. All right, it's a loaded coin. It's going to land on heads more. Use the binomial formula to calculate the probability of exactly 2 heads out of 3 trials. So what this would mean in the context of the question here, we would have 2 successes out of 3 trials. So if we're filling all that in, we'd have C, we'd have 3 and 2. The way we type that into our calculator, which we'll do in a moment, is we press 3C2. We're multiplying that by the probability of success. So the probability of a head is 0.53. It's the power of the number of heads, multiplied by the probability of failure to the number of failures, 0.47. So we'll show you how we come up with that syntax for our calculator. Basically, the only thing we need is C, which is combinations. So we'll touch on in term 3 in semester 2 of Year 11 methods. So in your run map, we'll press Option, we'll press across, prob, and then NCR. All right, and so that means what we have to do is type in the 3 before it. We have to go 3C2, and then we just type in this expression here, times 0.53 squared times 0.47. All right, now we've got 0.3960. Now for this whole unit, I think I'm going to try and remember, right to 4 figures and then round to 3. All right, very good. Okay, B is very similar. Any questions about A? So B says, what's the probability of getting 6 out of 10, 6 heads out of 10 trials? So this is 6 successes given 10 trials. So we're going to be doing 10C6, probability of success to the number of successes, probability of failure to the number of failures. And we'll evaluate that. C6, 0.53, power 6. All right, we've got 0.2271. Okay, the probability of 1 tail out of 4 trials. Okay, so if we're having 1 tail, that means we're having, now the definition of success and failure doesn't matter. We can define it as having one success and the tail as a success, or we can think of it as 3 heads out of 4 trials. It doesn't matter, they're both going to be the same. 3 heads out of 4 means you've got 1 tail. So we could have 4C3, 0.53 to the power of 3, 0.47 to the power of 1. That would give us three heads, which means one tail. And we've got 0.2798, which becomes that rounds up, so we get 0.280. Okay, and then lastly, it asks for a specific outcome. It says, what's the probability of getting heads, heads, tails, heads? So it has a particular order, heads, heads, tails, heads. Well, what this would require is us to get heads first, so 0.53, and then heads again, so 0.53, and it's conditional, so we're multiplying those events together, and then tails, so 0.47, and then heads again, 0.53. Okay, so that's what we're going to evaluate. And if we do this and round it to 3 sig figs, I'll just do that quickly in my head, we'll get 0.07. Interesting. Question is, why is this answer different from part C? Okay, because what we've got here, we've got one tail here, this is one tail, and this event here is also one tail. Why is the probability different? Any ideas? Oh, everyone knows. This is a specific order, whereas this doesn't matter about order. And if we think of having one tail, the way that that can occur is you could have heads, 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 tail, heads, heads, tail, heads, heads, tail, heads, heads, or tail, heads, heads, heads. In fact, there are 4 ways that that can occur. And interestingly, if you type this, just that part in, it's going to equal 4, because that's the number of ways that that can occur. And what do we also notice is that 4 times 0.07 gives us that 0.28. That each of those has a probability of 0.07 of occurring. This is one particular outcome. So that's what we would say for part D. The difference in C is that it's a specific order. Sorry, D is a specific order, whereas D doesn't matter about the order that the tail pops up in. Okay, now just the only other thing I'd say about that question is that we can use binomial formula very clearly because the probability remains the same. Every time you flip the coin, the probability of it landing on heads is not changing. It remains 0.53. Okay, let's move to question 2. We have a lucky dip contains 6 chocolate bars and 4 veggie delights. Now we might just simplify this question a little bit to so that rather than drawing it out, maybe we can't. We'll see. 6 chocolate bars, 4 veggie delights. Sounds yum. So Wendy draws from the box 3 times without replacement. Okay, so without replacement. Now what that means to us is that the veggie delights from the chocolate bars inside the box is changing, which means it's not independent. The trails are not independent, so no binomial distribution does not apply because there are the probability is changing. And we're going to demonstrate that in a moment with a tree diagram, like it asked us to do in part B. Okay, part B says to draw a tree diagram. So a tree diagram just illustrates the possible paths that you could take if you're picking 3 things out of the box. So from your first pick, you could either get a chocolate or a veggie delight. Okay, they're the 2 options. And we have 6 out of 10 chocolate bars, and we have 4 out of 10 veggie delights. So you're more likely to get a chocolate bar, but it's not guaranteed. All right. Now, now you're picking out 3 things. Okay, so if we pull a chocolate bar out, that means there's 9 things left over. 5 of them would be chocolate bars, and 4 of them would be veggie delights. Okay, so if we pull a chocolate bar out and then we reach in again, we could get another chocolate bar, but this has a probability of 5 out of 9. 5 out of 9 because there's 5 chocolate bars left out of 9 bars in total. We could get another veggie delight that has a probability of 4 out of 9. Okay. Now, I don't know how slow to go here. I'll just make sure everyone understands. If we've got a veggie delight, we could then get a chocolate bar, in which case that would be 6 out of 9, or we could get another veggie delight, which would be 3 out of 9. Okay, and we'll keep going. All right, we've got 2 chocolate bars. The probability of getting a third chocolate bar would be 4 out of 8, and getting a veggie delight would be 4 out of 8. All right, I'll just fill the rest in. So we'll have 4 out of 9. So what would that be? 5 out of 8, 3 out of 8. Chocolate, another veggie, chocolate, another veggie. So that's going to be 2 out of 8, 6 out of 8. And then we've got 6 out of 9, 5 out of 8, 4 out of 8. Okay, at every step, every I suppose split, the sum of the probabilities has to add to 1, right? 5 on 9 plus 4 on 9, that adds to 1, that adds to 1, that adds to 1, that adds to 1. And what we can see is, you know, the number of veggie bars going down here. Here we went a veggie bar, then we got a chocolate bar, so we've taken away 1 of each. So that's how we're generating all of those numbers. All right, so sketching is a bit of an arduous process, but pretty straightforward, I think. If you want to practice that, I can set you up with some resources. So we're going to use the tree diagram to answer these questions. What is the probability of getting all chocolate bars? Now, all chocolate bars means we get a chocolate, and then another chocolate. So we're following a particular path along our tree diagram. We're following this path here. Okay, so chocolate, chocolate, chocolate. And so then those events, we're going to just multiply those probabilities together. We have 6 on 10 multiplied by 5 on 9 multiplied by 4 on 8. So what's that?
1 on 6.
120. 120 on 720, 1 on 6. Just do that quickly in your head.
Yeah.
Thank you. Okay, then we have all veggie delights. So that's going to be veggie, veggie, veggie. So that's going this path. So that's 4 on 9 times, 4 on 10 times 3 on 9 times 2 on 8. So on 720, we've got 1224. Divide both by 12, presumably. Anyway, we can work that out in a bit.
1 on 30.
1 on 30. And then, what is the probability of 2 chocolate bars and 1 veggie delight? So if we have 2 chocolate bars and 1 veggie delight, there's a number of ways that this could happen. All right, so we've got to consider all of the ways from the tree diagram. It could go like this: chocolate, chocolate, veggie. So that's one of the paths. It could go chocolate, veggie, chocolate. Or it could go veggie, chocolate, chocolate. So we've got 3 paths that we need to consider there. We're going to calculate the 3 paths and add them together. What you'll also notice is that each path has the same probability of occurring. All right, so if we're going to go chocolate, chocolate, veggie, that's 6 on 10 times 5 on 9 times 4 on 8. And all other arrangements will have the same probability. So what we can do is calculate that and then just multiply
1 on 6. Well, 3 times 1 on 6.
Good, so which gives us half. All right, so the probability of getting a chocolate, chocolate veggie is half. 2 chocolate bars and a veggie delight. Okay. Alright, so let's move on to 3 then. As in the problem above, consider now a lucky dip operator who's going to replace whatever's drawn. Alright, so let's say you pull a chocolate bar out, it's going to immediately get replaced, which means now the probability remains the same. So part A, describe why this is a binomial distribution. We just say now the probability remains the same for each trial, therefore the binomial distribution can apply. Okay, part B. Using Pascal's triangle, expand P plus Q to the power of 6. Okay, so we've done this in Year 11 methods, but let's do a quick refresher. I'm just going to take the 5th row of Pascal's triangle and the 6th row. We've got the 5th row here drawn for us, 10, 10, 5, 1. And so then the way we would generate the 6th row is the sum of the two above, 15, 20, 15, 6, 1. So that's going to be the 6th row. Now, if we expand P plus Q to the power of 6, we just start with this coefficient. All right, so we're going to have one lot of P to the 6. Okay, now technically it's 1 times P to the 6, Q to the 0. All right, then what we do is we go plus, and then we take the next coefficient, which is 6. So that's from the 6th row of Pascal's triangle, 6. And all we're doing now is we're going to have P to the 5, Q to the 1. So what's going to happen as we progress through is that the power of P is decreasing by 1, and the power of Q is increasing by 1. So then we'll have plus 15, we'll have P to the 4, so notice P, 6, 5, 4, and Q to the 2. Q, 0, 1, 2. All right, let's smash it out. Plus 20, P to the 3, Q to the 3, plus 15, P squared, Q to the 4, plus 6, P, Q to the 5, plus 1, P to the 0, Q to the 6. Okay, splendid. Okay. A success is when Wendy gets a chocolate bar. Provided there are 6 trials, use your expansion in B to find the probability of Wendy getting all 6 chocolate bars. So what that means is P is the probability of getting a chocolate bar, which we know is 6 out of 10 or 0.6. And if we get 6 successes, all right, that means we have this event occurring. We have 0 failures, 6 successes. So our calculation is going to be 1 times 0.6 to the power of 6 times 0.4. 0.4 is Q, it's the probability of failure, to the power of 0. Now, all this will simplify to is, of course, 0.6 to the power of 6. And the reason is, any number to the power of 0 will simplify to 1. 1 times 1 is 1, so you can just imagine they're just disappearing. So we have 0.6 to the power of 6 for part A.
Why is it times by 1?
0.06. Why is there a 1 there?
Oh, wait, yeah.
Yep. So 0.046, 6, 5. Okay, so we write the first 4 non-zero numbers, and the 5 will round, which gives us 0.0467. So just emphasising those rounding skills. All right, exactly 4 chocolate bars. So if we've got 4 chocolate bars, that means 4 successes. That's going to be this event here. Now, what this number tells us is that there are 15 ways of getting 4 chocolate bars, right? You could get chocolate, 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 veggie, veggie, chocolate, veggie, chocolate, 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 veggie. Like, there are lots of ways it could happen, and it'd be really annoying to write out all of those iterations. There's 15 ways it can happen. So instead, we just go 15 multiplied by, we have 0.6 to the power of 4, and we have 0.4 to the power of 2.
0.311.
I like this. I don't know. 0.311. All right, so that number 15 then, that means the same as 6C4. If you type that into your calculator, you'll get 15, right? We should be seeing the binomial distribution formula here. P to the power of number of successes, Q to the number of failures, and this number comes from Pascal's triangle. mathematical, right? But it is the number of ways we can have 4 successes given 6 trials. Okay, so that's 2, and then part 3 says exactly 2 veggie delights. Well, that's the same as this event, right? 4 chocolate bars means 2 veggie delights. So our answer for this is all part C. C part 1, C part 2, and then C part 3 is going to be the same, 0.311. Really good. Okay, how many possible ways are there of getting 5 chocolate bars out of 6 trials? Okay, that's it. That's this one here. List all of the possible combinations. Who wrote this notes book? So we could get chocolate, 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 veggie, 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 chocolate, chocolate, chocolate. So we're just being methodical, just cycling it through chocolate, veggie, chocolate, 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 and veggie, chocolate, chocolate.
I think you missed one.
Sweating. Okay, calculate this and interpret its meaning. Alright, so if we evaluate C6, 3.6 to the power of 3, 0.4 to the power of 3, we will get 6C3, 0.6 to the power of 3, 0.4 to the power of 3, 0.2764, which is 0.276. Okay, which means the probability of getting 3 chocolate bars and 3 veggie delights from 6 trials is 0.276. Alright, so to interpret, three choch and 3 veg. Okay. What is the probability of getting 3 chocolate bars in a row followed by 3 veggie delights? So that's asking for, it's not that there, but this specific outcome, right? Chocolate, 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 veggie, veggie, veggie. So that's going to be 0.6 times 0.6 times 0.6 times 0.4 times 0.4 times 0.4, which is the same as 0.6 to the 3 times 0.4 to the power of 3. .013. Very good. Excellent. Okay, so why is that different? This is a specific order. In fact, getting 3 chocolate bars and 3 veggie delights, there are 20 ways that can happen. And this is one of those 20 arrangements. And if we multiply this by 20, we would get that same probability that we had over here, the 0.276. Okay, really good. So that's 7G.1. Let's lead into it.